Ladies and gentlemen, welcome back to Engineering Dynamics. In this video, we will be talking about an exercise in the field of vibracoacoustics, and especially how to work with the Helmholtz equation to get the eigenfrequency of a system where we have, for example, a tube that is fixed on one end and open on the other hand, and see what are the eigenfrequencies. So let's jump right in. A small recap from our derivation videos. We are now focusing on a Eulerian approach, so we're not looking at the Newton approach for one specific particles, but we're looking at a package of particles. We talked about the Navier-Stokes equations on how to get the Helmholtz equation, but we assume that we have no viscosity, and we linearize those equations to get the Helmholtz equation. So the linearization comes from the steady state. So we said that we're focusing on a steady state and we're dropping all the terms that are of higher order. And we said that we assume a adiabatic relationship that if we have a increase in pressure, there will be a increase in temperature, but that change of temperature is going so fast that it is not enough time to heat up the particles on the left and right of the high pressure area. And this led us to the Helmholtz equation, where we have a twice derivative in time is equal to twice the derivative, or this is the Laplace operator, of our pressure. And we said that, well, if we have a pressure gradient, it is equal to the speed or to the acceleration of our particle. So we said that if a particle feels a higher force on the right side than on the left side, it will move from right to left. So if we have a pressure gradient, we will see that the particles start to accelerate. Now let's look at our system. We have this tube that is open at the beginning and closed at the end. So given that system, we already know our boundary condition. So the pressure at x is equal to 0. So at the open end is P0. And we say that it is 0 because we're solving for the perturbation and not for the actual pressure. Then we see that if we have a closed end, that at this point in time, or at this point on our tube, our particles will never be moving, because if they move to the right, they would move into the wall, and that's not possible. And if they move to the left, they would create a vacuum, which is also not possible. So we say that the velocity of this particle is 0, which means that the pressure gradient at that point is 0. We propose an analytical solution of our Helmholtz equation, so for this one right here, and say that our pressure is some pressure function times our modulation function, so our time function. We perform separation of variables, basically. So now we have a derivative in time and a derivative in space. We derive it twice with our time function, so we get it from here. And this will lead us to a minus omega times the same time function we had in the beginning, because we go from sine to cosine to minus sine. So this is how we get the minus. For this one, we now have to propose a function. So this pressure that we have to derive it twice, and this should be equal, or plus that should be equal to 0, and fit our boundary conditions. So we propose a function, so the solution for our pressure. We say that we have some amplitude A times cosine plus B times sine. And from this part, we get our omega divided by c. So this one right here, because this is the only function that if you derive it twice will fit to this condition. Now we have to insert our boundary condition. So our boundary condition, the first one is that we have an open end. So we say the pressure at x is equal to 0. If we insert x is equal to 0, the cosine will turn into 1, but it should be 0. So a, we know from that a is equal to 0, and we can remove that part. A is equal to 0. Now we have to derive it once and get the pressure gradient and say that the pressure gradient at the end of our tube at x is equal to L is equal to 0. So we are left with this derivative. So if we derive sine, we will get cosine. And we could say b is 0, but that's a trivial solution and we're not interested in that. We are interested in what does our L and omega divided by c have to be 0. And we see that our cosine is always 0. Let's draw a cosine. When we are at, this is pi divided by half. So pi divided by half plus every pi, we will get a new 0. So this is our function or our values that will set our cosine to 0 and fit our boundary condition. So, and this is true for n is equal to 1, 0, and 2. So now we can say that our pressure is some amplitude, that is for now not important, times our sine, and we insert our equation from here times our x. So this is our omega. Oh, sorry for that, that's wrong. We have this one right here times x. So omega divided by c is, the L moves to the right, is this equation. So we now know that the pressure will have a function like this. The b can be now, for now, just ignored because this is just a modulation constant. Now we can say, well, what can we do with that? And we could say, well, how long, for example, does the tube have to be to get a eigenfrequency of 122 hertz? So if we have just the first excitation frequency, the first excitation that we chose from here. So we can change L. So we say that hertz, we have to transform it into radians. So we multiply it by 2 pi, and this will be our eigenfrequency. And from that equation right there, where we said n is equal to 0, we will get this equation, where we also have to know the speed of sound. And we just divide the speed of sound by our 222 times pi divided by 2, and we will get to approximately 40 centimeters. So if we have a tube that is 40 centimeters long, we're in the one-dimensional case here, where we assume the pressure in the y direction is always equal for one y direction, and we choose the first excitation where n is equal to 0, we know that our tube has to be 40 centimeters long. I hope this video gave you a better understanding on how to work with the Helmholtz equation. It's really not that difficult as soon as you understand it, but getting to understand it might be a little bit difficult. If you have any questions, feel free to ask them in the comments down below. Thank you very much for your attention, and I'll see you next time.